page 74, section 1.1. All right, so we want to look today at the definition of a function. All right, a function is just a special kind of a relation. Great, what's a relation? Well, a relation literally is just a relationship between two things. You could express that with a table of values or a graph or an equation. Probably most commonly we would think of something like y equals 3x plus 2. That shows us the relationship between x and y. But you could come up with all kinds of different relationships. Like there's probably a relationship between the amount of time you spend studying your vocabulary terms and the grade that you make on your vocabulary quiz. There is probably a relationship between the speed that you typically drive and the number of tickets that you have. There is probably a relationship between the population in Savannah and the year that it is. So we could take all kinds of different scenarios and represent them, those different types of relationships. A special type of relationship then is a function. And they tell us here in the textbook on the bottom of page 74 that if you have a function, each element in set A must be matched with an element in set B, where they're referring to set A as the domain and set B as the range. Okay, so basically every value in the domain has to be paired with the value in the range. Now, when we think of domain and range, we typically just think of X and Y. And that's fine until you get to a situation like the population in Savannah over a course of time. There's no X and Y in that. There's a P for population and there's a T for time, and I don't know what's domain and what's range. And so a little later on in the lesson, we'll be talking about the independent variable and the dependent variable and how we can kind of use those to help us figure that out. But in essence, when we talk about y is a function of x, or y is equal to 3x plus 2, x is the independent variable. Y depends on x. I can put anything in for x that I want to, and y will be determined by that. Y depends on x. So y is the dependent variable, x is the independent variable. So if we tend to associate x with domain and y with range, then we could associate the independent variable with the domain and the dependent variable with the range. So if we go back to our situation where we're talking about the population in Savannah, okay, does the population depend on what year it is, or does what year it is depend on the population? Yeah, the population depends on what year it is. I don't get to change the calendar, right? I mean, I don't control time. So the population depends on what year it is. So population would be the dependent variable. And we would think of it as the output, as the range, similar to our y value. The year would be the independent variable, and we would think of it as our input or our domain, or something similar to our x value. Sometimes instead of giving me like a word problem scenario, they might give me a graph. So just like you graph x on the horizontal axis, you're going to graph your independent variable, your domain, on the horizontal axis. And just like you graph y on the vertical axis, you're going to graph your dependent variable or your range on the or on the vertical axis. So they might give you a graph of some type of information, and by looking at the horizontal and the vertical axes, I can see what's independent, what's dependent, or what's domain and what's range. Okay, so they give me another scenario here on the bottom of page 74. They talk about temperature and the time of day. So does the time of day determine what temperature it is, or does what temperature it is determine the time of day? What time it is determines how hot it is outside, right? So that means that our temperature would be the dependent variable and our time would be the independent variable. So you can see here on the bottom of page 74, they've gone through and they've matched up several different times of the day with the temperatures. And you'll see that they're using the time of day as the x value or as the independent variable, and they're using the temperature as the y value or the dependent variable. So those times would be our domain values, our input values. Those temperatures would be our range or our output values, okay? So they say that each element in set A, in that domain, in that time of day, must be matched up with an element in set B. Every X has to have a Y. Every X has to have a Y. So at every time during the day, there's going to be a temperature to go with it, right? It can't be 5:07 and there not be a temperature outside. But the converse of that is not true. It says some elements in B may not be matched up with any elements in A. So there are definitely going to be some temperatures that don't get matched up with times, right? As bipolar as Savannah is, it's still not going to be 20 degrees and 105 degrees in the same day. We're not going to use every possible temperature. So all of the X values will be used, but all of the Y values do not have to be. The third thing it says is two or more elements of set A may be matched with the same element of set B, but the converse of that is not true. An element of A cannot be matched with two different elements of B. Here's an easy way of saying that. No two X values the same. You can have two Y values the same, but you cannot have two X values the same. Okay? So let's try and simplify this down because we've got a lot of different terminology going on in here. And we've got a lot of different definitions going on in here. So a function is a special type of a relationship where no two X values are the same and every X has to have a Y. The converse of those things are not true. Every Y doesn't have to have an X. I can have two Y values that are the same. The only stipulations are no two X values the same and every X has to have a Y. Okay? So we've talked before about the importance of multiple representation of functions and how this book is phenomenal about that and in getting us ready for AP Calculus, where we have to be able to represent functions in 4 different ways. We have to be able to represent them verbally, numerically, graphically, and algebraically. So in examples 1 and 2, they're going to go through and represent functions in each of those 4 ways. So the first one is verbally. It says the input value X is the number of representatives from a state, and the output value Y is the number of senators. Does that represent a function or not? Okay, well, let's see. Is every X going to have a Y? Is every state going to have representatives and senators? Yes, so that one's good. No two X values the same. If you go back to your government class, you'll remember that the number of representatives depends on the size of the state. So it varies from state to state, whereas the number of senators stays the same. So yes, that is going to represent a function because no two X values are the same and every X has a Y. It doesn't matter that I have two Y values the same. That's not a problem. Look at the next one. For the next one, they give me a table of values, so they're representing this numerically. If you'd rather take that table of values and rewrite them as ordered pairs, you can do that. So looking at the table or the ordered pairs, is this a function? Why not? I have two X values that are the same. Look at the next one. For C, they give it to me graphically or visually, in the form of a graph. And again, if you wanted to, you could go through and pull out the ordered pairs and write them that way. Is this one a function? Yes. Yep, every X is matched with the Y and no two X values are the same. We had a way that we used to be able to tell from a graph whether it was a function or not. Do you remember what that was? You could look at a graph and know whether it was a function or not. It was a test that we had. Yes, vertical line test, exactly. They're not going to teach that to me for another day or two, but if I hit something like C, it would be really helpful for me to just be able to go through and go, okay, when I draw a vertical line, do I hit my graph in more than one spot? No? Okay, then this is a function. Right? Look at example 2. For example number 2, right above that on page 76, they give you that terminology that we were talking about, the independent variable and the dependent variable, and a little more discussion on that. So again, remember we said the independent variable would be like our X value, it would be like our domain, it would be our input, it would be graphed on the horizontal axis. Our dependent variable would be our range. It would be like the y value. It would be our output. It would be graphed on the vertical axis. So example 2, it says, which of these equations represent y as a function of x? Now, if you knew what the graph of that looked like, you could just sketch the graph and do vertical line test, right? So when we hit problems like example number 2 on our quiz over this material in 2 days, I will give you functions that you already know how to graph. So like we've already learned how to graph lines and circles and that kind of stuff. I would give you something that you already know how to graph, so if you would prefer to just sketch it and do the vertical line test, you could. If you would prefer to do it algebraically, here's what they suggest. They tell me to solve the equations for y, and here's what I would want to be looking for. No two x values the same, and every x has a y. So I'd want to make sure that when I solved, I wasn't getting like some kind of imaginaries or something so that x wouldn't get paired with a y. Every x needs to have a y. I also want to watch and make sure I don't get two x values the same. And here's where you would see a flashing light. When over here, if I solve for y, I get plus or minus. Just because you get plus or minus doesn't automatically mean it's not going to be a function, but it should throw up a flashing light to you that, hey, I need to investigate this a little bit further. Because think about it. I picked an easy number like 3 to plug in because it gave me square root of 4, which was 2, so that was an easy value for us to work with. So I just picked a random independent value for x. I plugged in 3 for x, and that determined the value for y. I got plus or minus 2. So that means when x is equal to 3, it's equal to positive 2 for y, and when x is equal to 3, it's also equal to negative 2 for y. That's two x values the same, right? So again, just because you get plus or minus doesn't automatically mean it's not going to be a function, but that definitely is something that we would need to investigate further to check and make sure we're not going to get two x values the same. Okay? So again, you could sketch the graph of that and do vertical line test, or you could work it out algebraically, whichever you prefer. All right, bottom of 76, they talk to us about function notation. Function notation. If y is equal to 3x plus 2 is a linear equation, if you replace y with f of x, because y equals f of x, that's they're equal terms, so I can substitute. I can replace y with f of x since they're equivalent. So if I rewrite y as f of x and now I have f of x equals 3x plus 2, magically that becomes a linear function. So literally everything that I've already learned about linear equations, I can utilize for linear functions. So creating the equation or finding the slope or sketching the graph or any of those things that I already know how to use with linear equations, I can use with linear functions as well. They are going to use a special function notation though, and you'll see it here like f of 2. When you see f of 2, that doesn't mean f times 2. F of 2 means put 2 in the place of that x right there. So if I put 2 in the place of that x right there, that would be 3 times 2 plus 2. That'd be 6 plus 2, that'd be 8. That's what they want me to do with that function notation. So for example 3, we've got g of x is negative x squared plus 4x plus 1. So when they give me g of 2, what do they want me to do? Yeah, put 2 in the place of x. Now, when I put 2 in the place of x, is that negative going to get squared or just the 2? Just the 2. If they wanted that negative squared, they would have put it in parentheses. So I'm going to have a negative of 2 squared plus 4 times 2 plus 1. All we did was put 2 in the place of x. So what do you get for g of 2? When you put 2 in the place of x, what do you get? 5. All right, how about g of t? What do they want you to do when they say g of t? Put t in the place of x, exactly. So I could go through and just put t in the place of each of my x values, and I'll end up with negative t squared plus 4t plus 1. If they tell me to do G of triangle, I'll put triangle in the place of X. If they tell me to do G of smiley face, I'll put smiley face in the place of X. It doesn't matter what they give me. So when they give me G of X plus 2, that just means put X plus 2 in the place of X. So I could go through then and I could say, okay, I had a negative X squared. So we've put X plus 2 in the place of X. Plus 4X. So we've put X plus 2 in the place of X. Plus 1. And then we can just simplify as normal. So how would you simplify that? Okay, so we're going to FOIL that X plus 2 squared literally means X plus 2 times X plus 2. And yeah, also distribute that 4 to the X plus 2. Then what? Distribute the negative, right, and it's going to change every one of those signs, right? And then we could just combine our like terms. So that's our function notation. All right, last thing we want to look at today on the bottom of page 77 is a piecewise defined function. A piecewise defined function is exactly what it sounds like. It is a function that's being defined in pieces, right? So what it's saying is, this is your function f of x. We want you to use the piece x squared plus 1 if you have an x value less than 0. And we want you to use the piece x minus 1 if you have an x value greater than or equal to 0. You will not use both pieces for one singular value. Like when they give me f of negative 1, I'm not going to plug negative 1 into the first piece and negative 1 into the second piece and give two different answers. That's not what it wants me to do. F of negative 1 literally means put negative 1 in the place of x. So if I put negative 1 in the place of x, is negative 1 less than 0 or is negative 1 greater than or equal to 0? Less than 0. Since negative 1 is less than 0, that says then use this piece of the piecewise defined function. Use x squared plus 1. So I can take my negative 1 and plug it into x squared plus 1. All right, f of 0. For f of 0, am I going to plug it into the top piece or the bottom piece? The bottom piece, right, because I'm putting 0 in the place of x. So they said that if x was greater than or equal to 0, 0 equals 0, then they wanted me to use this piece. So I'm going to use x minus 1, and I'll put 0 in the place of x. How about f of 1, top piece or bottom piece? Bottom piece, because 1 is greater than or equal to 0. So I'm going to use that bottom piece of the equation, so I'll plug 1 in the place of x. All right, so here is our homework for the first half of section 1.1. For our quiz, it is over P5 through the first half of 1.1. So this is where the material will stop for our quiz.